For the next bit, we're going to be talking about Terraform, the issues we faced when scaling it to hundreds and hundreds of deployments, and how we fixed it to perhaps show you how you can make your job a little bit easier. So first of all, show of hands, how many of you manage your infrastructure as code? So that is any system programmatically, all right? And how many of you do so with Terraform? Good, good. That's about 3/4 of the room. So we're all familiar with the benefits of infrastructure as code. And while Terraform is perhaps the best tool at the job, arguably, scaling it to hundreds and hundreds of deployments is where it started to fall short for us. So we're going to show you what we did instead, which not only sets you up with a sustainable scaling pattern to scaling your own deployments and your infrastructure, but also makes the developer experience much better for your Terraform users, all while plugging into your already existing Terraform automation. So hi, I'm Ricard. I work at ThousandEyes, and I'm a site reliability engineer, your speaker for this talk. So I'm going to run you over to about what the problem is that we faced when scaling Terraform. And to do so, I'm going to show you the usual Terraform lifecycle, so to speak, when you start using Terraform. This is the usual Terraform deployment. You write some code, you run Terraform, and boom, you now have infrastructure. Great. And this works great for a little while. Every change you want to make, everything you want to add, it's just as simple as modifying that code base. And that works great for a good while. But then one day you're asked to scale that up, right? You need to do that again. And you can do it by, you've done it once, so you can do it twice, right? You can just copy paste the code, but you know better. You put everything into modules, which is the right thing to do, and just call that module twice. Once for prod and once for staging, for example. And again, this works great for a little while, but then you scale it up again. And when you do so, it can be any other different environment, right? It can be an EU environment in a region for data locality. It can be deploying to, I don't know, a customer's house because they want your software in their house, or just another testing environment for a chaos engineering test. But thing is, your infrastructure grows, right? And here is where you start seeing the problem with Terraform, the very first one. And that is, at some point, your plans just start taking forever. And you're familiar with this, right? So any single change will trigger a plan. And every single plan will trigger a refresh across every other resource you have in your infrastructure. So at some point, when you have enough resources, that's going to be way too many API calls to your providers, and that's going to take way too long. And sure, there is an option in Terraform Plan to disable refresh, but it's impossible to disable that without risking making a plan that's based on an outdated picture of what reality is. State on Terraform is just a picture of what it looked like the last time we looked, but that may be outdated. Something might have changed, and you don't want to risk that. So the real solution you have out of this really is to just split things up. So if you used to have a big deployment with thousands of resources, you break things down into a bunch of deployments. And you can pick whatever cardinality measure you want this, whatever dimension you want. That can be production and staging. That can be region. That can be, say, workload, so VPCs, clusters, and databases. You can choose any combination of all of those. But the thing is, you end up splitting your Terraform deployments into smaller deployments so that state is not that large, and so refreshes don't take that long. And here is where we started seeing the bigger problems. And number one is you're opening up the door for drift to creep in. And the reason being is different deployments must have different files. And those different files should in theory be equal, right? The state backend is always the same. The provider config is always the same. The production staging cluster should ideally be similar. But truth is, they are different files. So they can contain completely different pictures of what infrastructure should look like. And so this is what we call drift. And fixing drift in Terraform is awful for a number of reasons, right? So number one, you only have two ways out of fixing drift in Terraform. The first one is just go into the state and do what we call state surgery, right? Which is basically just Terraform importing and state removing stuff to undo your steps back whenever you have drift in your system, right? So at some point, right, you have all your deployments, say, brought in staging, but in 1 year from now, you realize, hey, we have a database in staging that is not in production, and the reason for that is someone forgot to put it in prod, or the other way around, or there's this parameter that's completely different. And so by doing that, what you need to do is you plug into the state and then reconcile all of those steps. But the problem with that is in Terraform, every resource can depend on each other. So the complexity of doing that does not scale up linearly. It scales up exponentially because you need to retrace each and every one of those steps back in order to go back to a decent state. And if you don't like that, then really the only option you have is to just run a plan and run with it, right? Take whatever it outputs and just destroy, recreate whatever Terraform proposes so that your state now matches again what the desired reality is. So that's no good. And to make things worse, you also open up the door for boilerplate to proliferate across your code base, right? Because if you have, say, 20 deployments that should all do the same, right? They should all deploy the same VPC just on a different account or region, then sooner rather than later, you'll figure out that most of your code is just Terraform config. So that goes for the state backend, providers, variables, even module calls. They're all the same across all your deployments. There's only minor differences in maybe an instance count or some other smaller parameters like the name or the region. And all of that is just boilerplate. You don't want to put that into your code because then it's a mess to handle. So to sum things up, right? We first start with plan times. That's what happens naturally, organically, as soon as you start scaling up your infrastructure. That's to be expected. But then the only solution you have is to split things up. But by doing so, you open the door up for drift to creep into your Terraform state. And it gets to a point where it's completely unmanageable. And you don't want to be fixing Terraform drift. You want to be preventing it so that it never gets into the system in the first place. And then also a product of splitting things up, you start seeing your code base be filled with boilerplate and basically Terraform config that has nothing to do with your infrastructure. It's basically code that doesn't map to anything useful in all of your infra. So this doesn't scale. This will never scale, not like this. So what did we do? Well, before jumping into what we did, we first looked at what the available solutions were out there. And I'm only going to mention one of those, which is TerraGrunt. So TerraGrunt, for those that don't know, is basically a way of fanning out whatever Terraform code you want to as many deployments and instances you want of it, right? And that's good. It looked promising. The problem with that is, at the time, we already had over 5,100 Terraform files, all of which would have pretty much required a rewrite, and that was a hard no-go. But also, and very important, we operate in our team in a sort of provider-consumer kind of way, in that my team, the infrastructure team, provides Terraform as a tool for the rest of the SRE group to use and deploy infrastructure with. And so in a context where you want people to use Terraform more and not less, adding a tool to the mix and raising the skill bar is only adding friction, which will then hurt your adoption. So you don't want to be doing that. And then it also didn't solve our boilerplate problem, really, because it just added more boilerplate related to how TerraGrunt operates, right? All the TerraGrunt configuration that goes along the Terraform configuration. So we built our own, and we called it Stacks for Terraform. So let's go back to where we were, right? We've split things up. We have a number of deployments, all of which deploy different infrastructure that's basically the same, but in different regions or on different locations. And this is how pretty much everyone does Terraform today, regardless of how you got here. But this is pretty much the current state of how 99.9% of people do Terraform today. And so what Stacks does is it adds a layer of abstraction in front of it that lets you define a single code base for then you fanning out into Terraform. And this is similar to how TerraGrunt operates, but then it does a bunch of things that you'll see that TerraGrunt doesn't. So I'm going to show you an example of what a stack definition is. So that would be the orange code down there that you're passing over to Stacks. It will take a number of stack definitions. One of this, like an example of this, is the VPC stack. And then within a VPC stack or any stack definition, you have a base directory. Whatever you put in here goes to all your deployments of the same stack. So if you have a production and a staging VPC, whatever you put in those two files will go to both the prod and staging. Easy. And then you also get a layers directory. In the layers directory, you define one directory for every instance you want of that stack. We call these instances layers, hence stacks. And what you put in those is only local to those specific layers, right? So if you want a set of variables that's different from the production one in staging, you can just put that there. It also allows, which is something that we missed in Terraform, a arbitrary number of Terraform files in it so that you can also add differences to your different layers. So if in this case your staging VPC needs access from your developers, then you can also add, in this case, a VPN thing that lets them access it. But that won't go into production. And then you also get a stack.tfr that lets you define globals across all your layers, right? Here's where you would put the common variables that are common to all the layers in the same stack. And here's the workflow, right? So remember, stacks will take a number of stack definitions, like the one I showed you, and then it will pre-process that code and then pass it over to Terraform. So it takes the definitions, it joins the stack and layer code to produce the output code. It transforms it in a couple of ways. It injects some extra things that you'll see later. And then it bundles it up and passes it over to Terraform to take over. And so by doing this, we keep the same contract or agreement with Terraform all the time. That means we're not making deployments, as in Terraform deployments, any bigger or smaller. The same separation is kept. The same state size remains. So plan times are kept the same. So if you fixed your plan times by splitting things up, this won't make them last longer. So that's one. But then we keep drift under control. And here's where it gets very nuanced, because with the splitted deployments where you have a number of different files that all define, in theory, the same thing, but could be different, what we do is we keep the code inside, as in it's very obvious for me as a Terraform developer or for someone in my team as a reviewer to just go into my stack definitions, and whatever is in the layers directory is different between layers. So it's very easy to see what the differences are. And the reason you want to do that is because you don't want to be preventing drift. What you actually want to be doing is you want to keep it inside, because otherwise, what's the difference between drift and an actual desired difference between your layers, right? So the VPN thing, that's something that's different. There are needs, there are reasons we sometimes have differences between staging and prod, between an EU deployment or a customer deployment. And if we forbid that, then there's no way for us to do that. So we don't want to be forbidding any difference between deployments. What we want to do is we want to make it very obvious to keep them out of our system, right? So as a reviewer, it's very easy now to just go to the layers directory, and whatever is in there, just go through the logic of, is this something we want, or is this something that's drift, and that should be either removed from this specific layer or made common for all the other layers in the base directory. And then we also inject that boilerplate for you, and that has to do with the part where I explained the injection stuff. And this is where the developer experience we've seen gets much better, because now as a developer, the mantra that we always follow now is you should not be writing anything and putting anything that's in your repo that's not a resource. So now as a dev, when you're using Terraform at ThousandEyes, everything you do when you're using Terraform is just pushing resources to Git. You don't have to worry about configuring state. You don't have to worry about configuring providers. You don't even have to worry about declaring your own variables if you forget them. And so this makes it a breeze to work with Terraform. If you want an S3 bucket, it's as simple as pushing a paragraph with the S3 bucket declaration. That's all. No need for anything else. And it also has a very nice byproduct to me as a Terraform admin, in that I get to enforce some sort of uniform Terraform settings for state and providers that don't have to be in a rated kind of way. Like, I don't have to be asking people not to do things wrong. I just do it for them, and so they don't have to worry about it. So it's very easy for them to just forget about it, and to me, to maintain a uniform configuration across all my states, across all my providers, right? We have about 50 AWS accounts and about 20 regions on each. So that's easy 1,000 provider declarations. We inject all of them for you. You don't have to worry about any of those. And so that way, you cannot do it wrong. You cannot forget a default tag. You cannot mess up with the role ARN. And then it also has a number of extra features that we have seen have made our lives much easier. So I tried to shorten the list as much as possible, but this is what I got it to. So number one is you get a cascading variable scope. If you've used Ansible or some other tools that do this, you'll be familiar with this, right? You can define a variable for an entire group of hosts, but then if you need that variable to be different in one of the hosts of that group, you just override that with a host variable. Well, we do exactly the same with the stack.tfrs and layer.tfrs files. We even have a common .tfrs files that sits outside of the stack definitions and lets you define variables that are global for all the stacks. So that's one. Then everything we talked about, the automatically injected state backend and providers. Also, and this is a pretty cool one, automatically injecting your variables. So what does that mean? Well, in Terraform, if you use Terraform, you'll be realizing that in order to declare and define a variable, you need to do those two things, right? You need to push a Terraform file, a variables.tf file, that contains the declaration. And that will hold whether there has a default or the description, the name of it, the type, if you want that. And then if you want to assign a value to it, you would then have to push another file, a something.tfrs file, that assigns that value to that variable. We found that to be a little bit, I don't know, cumbersome. So what we thought is, how about we have stacks scan through your code, figure out the variables you want and the variables you declared. And then for those that you forgot, whether willingly or not to declare, we inject that for you so that you don't have to worry about it. And what this reinforces is the mantra of not pushing anything that doesn't have to do with real infrastructure, just pushing resources. So now, as a result of this, everything that's in our code base maps one-to-one to something tangible in real life in our cloud providers. Because we no longer have variables.tf that have like 20 declarations for stuff that have no other parameters. It's just declaring that the variable exists. Another one that we added fairly recently, and we are using more and more, that is secrets injection. You'll be familiar with this if you used YAML or sealed secrets in Kubernetes, in that you now, if you have a variable that has a secret value, but you want to put that value in your Terraform, you no longer have to be declaring a data source that pulls it from some external system or inputting them during the automation phase. What you do is we give you a public key, we give Stacks the private key, and then you just encrypt the value, put the output in your Terraform code, and what Stacks will do as a code preprocessor is before fanning your code out into multiple different deployments, it will also decrypt all of those values and put them there for Terraform to see as if they had been hard-coded along the way. And on that note as well, we added Jinja templating. And the reason for that is, if you've used Terraform long enough, you'll realize that there's some places where you cannot simply use variables, right? Things like module source or anything that has to do with dependencies, right? And the reason for that is the Terraform plan, when it runs, when it happens, the internal workflow of it, it first figures out what the dependency tree is for all the resources and modules, and only then it figures out what the values for the variables are. So obviously, you cannot use those values in building that dependency tree. But we don't have that constraint. We're just a code preprocessor. We don't care about dependencies. So what we do is, if you want to use a variable wherever Terraform wouldn't let you, instead of using the Terraform dollar and curly brackets, like variable substitution syntax, you replace that with the Jinja syntax, which is just double curly brackets. Everything else stays the same, the variable name, whatever you're doing. And instead of that being populated by Terraform, it will be populated by Stacks before Terraform sees it. So from Terraform's point of view, it's as if it were hard-coded all the way. But it wasn't. You can use a variable there now. This also helps with fixing some of the problems with HCL. So Terraform's HCL has it's declarative. And the problem with that is you sometimes, just sometimes, need to do imperative stuff. Things like, if such and such is true, then deploy this thing, otherwise deploy this other thing. The way you do that in Terraform is pretty hacky. You use some count argument, and then you just set that to 0 or 1, depending on the condition. Well, with this, you just put a Jinja syntax, like you just use the percentages and curly brackets, and then if true, put this resource in. Otherwise, either don't put anything or just put something else. You're free to use that however you want. And there are more features that I didn't just have time for covering. So here's what we would call our reference architecture after building stacks, right? So this is what we would do really, not only what we do now, but also what we would do if we were to start all over again, right? Because it has turned out really great, and we would be happy to run the path again. So we have a mono repo. Some people do, some people don't, but we have a mono repo with all our Terraform code, right? And it holds all our stack definitions for everything we have in our infrastructure. And then every time you want to make a change to it, you raise a pull request with the changes. And that pull request is picked up by Atlantis. Atlantis, if you don't know, is an open source tool that plugs into your Git or whatever repos you're using and automates Terraform for you, in that it takes whatever changes you made in .pr, and then it runs Terraform and posts the plan output as comments for everyone else to see and review. And then if you want to apply it, just go ahead, Atlantis apply as a comment, and then it will apply it for you, paste the output, and merge automatically. Well, what we have is we have Atlantis not only run Terraform, but before that, we also have it run stacks. So every time you make a change, you raise a pull request, Atlantis picks it up, runs stacks on it, generates the output code, and then it runs Terraform on that. And we also recently fixed an issue with Atlantis that had a race condition on the parallel stuff. So now we also enabled parallel plan and apply. So if we're changing, say, the base code for a stack that has 50 layers, which would be 50 plans, each taking, say, a minute, that's not 50 minutes. That's a single minute to plan all 50 of them. So we can change our entire infrastructure in, what, less than 5 minutes, and whatever it takes for an engineer to review. So that's pretty cool. We love that. So to sum things up, if I had to choose what goes out of this talk, is number one, Terraform is still great. With all its flaws, I do still think it's probably the best tool for the job. I don't think anything else has come close to it, even though it has a number of flaws. But when it comes to scaling up, the default scaling pattern of just using modules and copy-pasting every time you want to, just scale your infrastructure up, it only gets you so far, right? And think about it. If you have a production environment today using Terraform the same way everyone does, and you're asked to deploy, I don't know, a disaster recovery scenario somewhere else, what you're really doing is just copy-pasting the directory and changing a couple of variables. So you don't want to be doing that. That's just doing that drift thing all over again and adding boilerplate to the mix. So we need a better way to scale. And for us, code pre-processing has worked. That's what Stacks is. It's a code preprocessor. It just takes your source code, it preprocesses it into your output code, and then it feeds that output code to Terraform. It does nothing else. It's not even tightly coupled with Terraform. So in theory, you could apply it to some other tool if you have a similar use case. And just as of Friday, we've made it open source. You'll see it's very simple. You can use it. It plugs into your automation pipeline easily. You just need to run it before and follow the directory structure that I showed you before. And that's all. It's really that simple. For the developer, it's very easy because, again, if you want to have more infrastructure, if you want to modify anything, you just push the resources. You don't care about anything else. And if you want to have that 50 times, just have 50 layers. That easy. And with that, I'll open up the floor for questions.